For over 2,000 years, mathematicians have viewed prime numbers as irreducible building blocks of arithmetic. If you plot them on a standard number line, they appear as discrete points scattered across a one-dimensional path. We have global laws governing how many primes exist, but their local distribution remains resistant to prediction. When you look at where the next prime occurs, the sequence is indistinguishable from pure noise. But there is a growing hypothesis that primes are not physical objects at all. Instead, they might be the visible readouts of a deeper hidden system. To see that system, we have to throw out the ruler. We must stop treating the number line like a geometry problem and start treating it like a radio signal. If primes are an encrypted wave, then finding their underlying frequency reveals a structural order where we once saw only chaos. Tuning into this frequency requires a coordinate shift. We take the logarithm of the integers, an operation that converts the geometry of multiplication into the arithmetic of addition. This transformation stretches the standard number line into a new mathematical environment called log space. This is the Chebyshev residual graph. In log space, we stop counting individual primes, instead measuring this oscillating wave, tracking exactly where the count runs ahead of or behind the statistical average. This continuous fluctuation is the raw signal we analyze for hidden structure. Focusing on these fluctuations moves the problem out of pure number theory and into the analytical domain of signal processing. Once we have a continuous signal, we can apply a Fourier transform, the standard tool used to pull specific frequencies out of noisy data. Through the transform, the noise falls away, leaving massive frequency peaks representing the dominant rhythm of the primes. The spacing of these peaks exactly matches the Riemann zeta zeros. Every zero acts as a specific wave frequency operating within log space. Primes appear in our reality at the exact moments these invisible spectral waves overlap and constructively interfere with one another. This indicates that primes are resonance events generated by a structured underlying wave system. If this wave system is real, we should be able to track its peaks and valleys to predict future prime activity. The smooth predicted wave on the left forecasts the prime distribution on the right. Dense prime clusters perfectly align with the wave's peaks. Crucially, this predictor uses only the spectral wave, never training on the actual primes it predicts. For 160 years, primes were treated as random occurrences. This data suggests they are a driven, highly structured system. Rather than generating chaos, primes are simply sampling a highly organized, invisible oscillatory environment. The primes we observe are the visible peaks of a resonant mathematical symphony.